Okay, let's continue with exercise 2. So we've learned how to model the plane of array irradiance. But the plane of array irradiance by itself is not the actual input to our models. There's something else missing, or two things missing. First is also we need to also calculate the solar cell temperature, which has an impact on the efficiency of the solar panels. But the plane of array irradiance represents only the energy or the photons that reach the surface of the panel. So if you have soiling, even though you have, let's say, 500 watts per meter squared irradiance on the surface of the panel, and you have soiling on the front glass, and let's say that soiling reduces the irradiance by 50%, effectively only half of that, so 250 watts per meter squared, can reach the solar cells. So we have kind of a difference. We have the irradiance that reaches the panels, and then the irradiance that is actually absorbed and reaches the solar cells and the PN junction. And there are several things that can happen there that, ideally they are the same. In practice, there can be some differences, and that's why we make a distinction about the irradiance that reaches on top of the surface, which we call plane of array, and the actual irradiance that reaches the cell and the junction and is absorbed. And we call that one effective irradiance because it's being effectively absorbed. So one thing I mentioned that can happen is soiling losses from vegetation, from dust. That is basically, it's a barrier between the panel and the environment. Other things that can happen are reflection losses. So if your sun, for example, in this case, we have a very low tilt solar panel. If the sun is very low in the sky, you have a very high incidence angles. And as many of you know, if you have a very high incidence angles, you also start to have more and more reflection losses. Even though the irradiance reaches the surface, part of it is being reflected and only part reaches the solar cell. So then again, we have a difference between the irradiance reaching the surface and the irradiance that is being absorbed. Other things that can happen that we'll talk about is a little bit the spectral sensitivity of the solar cells. So some solar cells do not absorb the entire energy spectra of the incoming light. So even though some light reaches the top surface of the panels, they are only sensitive and absorb certain wavelengths. So when we want to calculate the actual output or input of the models, we need to calculate the effective irradiance from the plane of array by accounting for these different loss mechanisms, which will depend on the type of panels we have, their angle, their reflectivity properties, and their spectral responsivity. Well, and we'll get into that. As I said, the other variable we need to calculate is the cell temperature. This is a little bit more easier. So what does the cell temperature depend on? Well, it depends on how hot the environment is, so the ambient temperature. It depends on how much energy they receive from the sun. So because the sun is the one that is effectively heating up the cells. And we have some cooling. The wind is the one that provides convection and can cool the panels, both from the front and the back. So effectively, the cell temperature will depend on the irradiance, the ambient temperature, and the wind speed, but also depends on the thermal properties of the panels and of the panel packaging. So how thermally conductive is the front glass, the EVA. It will also depend on how the panel is mounted. if the panel is mounted on a roof and there's no gap between the roof and the panels, there's no place for the wind to come and cool it from the back. So they will be naturally a bit warmer. Now, we'll start first with modeling the cell temperature because it's a bit easier, and then we'll go into the effective irradiance. Once we've figured out how to calculate those from plane of array, ambient wind, and ambient temperature and wind speed, then we are ready to calculate the power that the panel and then an array can generate. And that will be the PV array performance model, where we calculate the power output of a PV panel or PV array based on the plane of array irradiance and the ambient temperature and wind speed. So let's start with the solar cell temperature. Now, we cannot measure solar cell temperature directly because the panels are laminated. It's either a glass or a glass sheet module, and they are laminated at high temperature, and it's difficult to put a sensor. You could, in principle, laminate the sensor. That would be expensive, but would also compromise the module packaging because we laminate the panels so they are watertight. So if we laminate the sensor there, it will create some air gaps and the panel will not be as tight. So we have no practical way to measure the cell temperature inside the panel. However, we are able to measure the module temperature on the backside. We don't want to put so we put a sensor on the backside. This is a surface temperature sensor that we need to basically glue using a thermal conductive paste. And we do this on the backside. We never put it on the front side because then the sensor will be heated up also by the irradiance. So we only want the sensor to be heated up by the panel themselves. So that's why they need to be mounted on the back, and they need to have good thermal contact, and they need to be kind of in the middle of the module and the middle of the cell. The backside module temperature is not exactly the solar cell temperature, is slightly lower by a few degrees. How much lower depends if the module is an open rack or if it's insulated and if it's a glass or a backsheet module. But the difference is of a few degrees. So if we can measure the back of module temperature, we can estimate what the cell temperature is quite accurately. However, if we cannot measure the backside module temperature, and often we cannot because sensor costs money, and especially if you have a lot of panels or a lot of strings, you cannot deploy sensors on each of them. So what you do, you can model this backside module temperature. You can model it from the ambient irradiance, the incident plane of array irradiance, and the wind speed. And then you have, this is one of the many models for back of module temperature. Then you have two material and construction parameters. These are empirical parameters that you need to choose based on the type of module packaging you have. So is the glass or a glass sheet? And is it open rack, so like a ground-mounted PV plant, or is it on your roof? And then is there some kind of gap in the roof? And based on the configuration you have and the type of material, then you choose the right parameters here. And then you can read a bit more about this model in this reference. For the solar cell temperature, as I said, we can estimate it from the module temperature that we model or we measure. And it also depends, of course, on the how sunny it is, because during the nighttime, when the irradiance is 0, the cell and the module temperature will converge to the same value. Whereas if the cells are heated on the front, they will be slightly hotter than the rear module temperature, and then you need to scale them with the irradiance. And then how much you scale them, again, depends on the module packaging, so this delta T, and the type of mounting that you have. So let's see a short demo on how to model the module and cell temperature for our system. So first I will initialize the environment, similarly like we did in the previous exercise. Then we have the same system parameters and data sets. I will load these ones. Then we'll need to define our temperature coefficients based on the type of module and the type of system. So the type of module that we have for this system is a TwInSolar module, and this is a glass backsheet module. And we know this because it's also an older module. For some of the panels, they will say, or for the newer panels, they say if it's glass, or glass backsheet. This one only has glass on the front and has a polymer backsheet on the back. And as far as how the system is mounted, if we have a look at the initial picture that we had here, we can, because the gaps between the panels and the building are quite high, we can consider this to be an open rack system. So that there's ample space for the wind to cool the panels from the back. So in this case, we'll choose a glass polymer sheet with an open rack. So we'll choose the parameters here. And that's what we have here. Then we load our weather data set. We calculate our plane of array irradiance on the two surfaces. And then we implement equations 6 and 7 to calculate the module and the cell temperature for the two surfaces. And then we plot it for a clear sky day. And then we have them plotted against the ambient temperature. So you can see with the blue, the ambient temperature goes up to 25 degrees. Then let's look at the northeast, which is the green and the orange. We can see that the back of module temperature is the orange. It reaches about up to 42, 43, whereas the solar cell temperature a little bit above 45. So there is a bit difference. So this is the actual temperature of the modules, even though the ambient is only 25. So in reality, modules operate at quite high temperatures. And then you can also see from the data sheet of the module, the temperature that the module is designed to operate under normal operating conditions is 45 degrees. And normal operating conditions is 800 watts per meter squared, 20 degrees Celsius, and just a little bit of wind. So if it's more irradiance or it's hotter, they will be even higher than 45 degrees. Okay. Now, instead of implementing the equation, so the ones that you see in equation 6 or 7, we can use some functions like there's different temperature models implemented in pvlib. The one that corresponds to equation 6 and 7 is called the Sandia PV array temperature model, which I don't know why it's not loading, but it's in the temperature package. It's called SAPM cell, where you need to provide the plane of irradiance, the air temperature, the wind speed, and then these three coefficients. Of course, there's several other models that are being used. This is one of the simplest ones that you can use. And if you can compare these two, the equations with the pvlib, they overlap, so they are exactly the same. So we have one of the model inputs down. We have the cell temperature. Let's see about this effective irradiance. So the kind of the three major losses that can happen between the plane of array and the effective irradiance is soiling. So we need to account for any kind of soiling losses by multiplying with the derating factor SF if there is soiling. Now, in the case of the interpost system, there's not a lot of soiling because you have quite frequent rains, although you have a very low tilt. So when you have a tilt of 9 degrees, dust tends to accumulate. So if it doesn't rain for a few days, you might have dust accumulating on the panels. And this is a problem for more desert areas near the equator or in where you have low tilt angles, but you also have a lot of dust and not a lot of rain. Then you need to account for the soiling factor. For Réunion is not the case as far as we've seen. The other thing you need to account for is the angle of incidence losses. So glass becomes has a certain reflection profile depending on the incidence angle. So if you have low incidence angles, the light is just transmitted through the glass. Whereas if your incidence angles becomes higher in comparison to the normal, so it's very shallow in comparison to the horizontal, the glass becomes more and more reflective and you start to have reflection losses inside the glass. And this is a kind of a material property. So different types of glass will have slightly different loss factors. So where you want to be with this angle of incidence losses at 1. So this is a derating factor. When you start to get at higher angles, then you start to have higher and higher reflections, and basically the photons do not reach the solar cell anymore. So in order to know how much losses, reflection, or angle of incidence losses you have during the day, you need to model your angle of incidence using a solar position model, but you also need to know the reflective properties of your glass to calculate this curve here. And there's models for this for typical solar glass. Now, if you have some special glass like satinated glass, or glass with different structures, it will have a slightly different angle of incidence function here. Now, typically, if you have optimized the angle of your system, that means that most of the time the incidence angle will be very close to 0. This becomes a problem for abnormal angles. So for example, if you have building integrated where the panels are at 90 degrees, then you can have, high incidence angles when the sun is high above in the sky. So then this becomes more of a problem. Now, the third aspect that you need to account for, especially if you're using solar cell technologies that are not crystalline silicon, is the spectral response of the technology. And this is more typical for thin film solar cells. And here we have a solar spectra, or the solar spectra shown in black, where on the x-axis you have the wavelength, and this is the spectral power or spectral irradiance, versus in color here is the spectral sensitivity of different technologies. And you can see silicon and CIGS are sensitive to a broad range where the most of the energy is, whereas technologies like cadmium telluride or morphosilicon is only sensitive to part of this. This is kind of the visible light where we get most of the energy. So in that case, even though you have the energy at the input, it is not being absorbed by the solar cell because it has a different spectral technology. And in that case, you need to account for that with this spectral mismatch factor. Now, to make things more complicated, This solar spectra, the black one, is not constant during the day. It changes with the position of the sun in the sky and also with the thickness of the clouds and the content of the clouds. And there's different models to account for that, and it can get complicated very fast. But to make the short story, you need to account for this whenever you have spectrally sensitive technologies like certain types of thin films. Then you need to account for that. Usually for crystalline silicon, we don't do this unless we want very precise modeling of the irradiance. Now, how do we model these things? So to make things simple, there's not a lot of soiling, so we'll not need to model this. We'll assume is 1. And since we use silicon technology, it's not so spectrally sensitive. So we'll assume that we have no spectral mismatch losses. And the only thing we'll model will be the angle of incidence losses here. And the simplest model to model these reflection losses is using the ASHRAE model, which takes as input the angle of incidence and a material constant that is depending on the properties of the solar glass. And you can either implement the equations or use the ASHRAE model inside of SAM and then use the value typical for most solar glasses. If you have something more special, then you need to determine what that one is. And then what we do, we calculate the angle of incidence, we calculate the IM losses, and then you can see if we plot this angle of incidence modifier, that is 1 for most of the day. But whenever the sun is lower in the sky, basically you are starting to be here. Then this loss factor becomes, or the derating factor decreases. So you are starting to lose energy in the morning and in the evening due to the reflection losses. And there's also a difference between the orientation of the panels. So we take this IM loss factor and then we apply it to our plane of array irradiance components, which we can access as POA direct and POA diffused. And then we calculate an effective irradiance. And we assume there's no soiling because there's a lot of rain. And since this is silicon, we'll assume this is 1 for simplicity. And then when we calculate these ones, we get something like this. This is what we would model just as plane of array, and then if we account for reflection losses. And you can see it's not a lot happening here. And in most cases, we don't even do this distinction. Unless you have either special glass or you are operating at extreme angles. So these kinds of angles and these kind of losses accumulate, or if you have soiling losses, which is not the case. So for most purposes, we usually just use POI irradiance and effective irradiance interchangeably. But if you really want to be accurate, then this is how you calculate it. So these are the inputs to our PV model. So what does our PV model model? There's different kinds. The simplest ones and the ones most often used model the PV array power output. So what is the power output? Usually the PV arrays are operated by an inverter with a maximum power point tracker at the maximum power point. This is the current voltage characteristic of a panel. And if you have the panel connected to the inverter will make sure that you operate at the maximum power point. So if you want to predict or model how much power a panel or a PV array will generate at any point in time for a given irradiance and temperature, you need to have a model that will estimate the PMP. And one of the simplest and most widely used models is called the power temperature coefficient model. And it has only 2 model parameters and 2 inputs. So the 2 model parameters actually just is the rated power of the panel. Okay, where'd they go? Sorry, it's the rated power of the panel and the temperature coefficient of the power. And the input variables are the effective irradiance and the cell temperature. And this is the model. This is a model for a single panel. So if you want to scale it to a full array, you need to multiply of how many panels are connected in series in a string and how many strings are connected in parallel. So this is the NS and NP that you might be familiar with. So how do we get these 2 parameters? Well, we go to the datasheet of the panel, and then we have the maximum power, the maximum rated power of the panel, and then we have the temperature coefficients. So that's why this model is very widely used. It's very easy to parameterize just having the datasheet, and you always have the datasheet of the panels. And then you can get like a fairly accurate model. The only limitation is that it only models the maximum power. It doesn't give you the full IV characteristic. You need to use a different model for that. Okay, so this being said, let's together try to model the performance of one of our arrays. So we'll try to model the performance of the array connected to MPPT1 of inverter 1. And we have in total 8 of these arrays, and they are connected to the different inverters and their different MPPT trackers. All the panels are of the same type. It's just there's different configurations. For example, the array that we want to model has 36 modules, where 18 panels are connected in series in a string, and then we have 2 strings in parallel for this input. And inverter 1 is connected to the northeastern roof. Now, to make things a bit more complicated, this is not a new system. This system was installed in 2008. What does that mean? Well, in 2008, when the panels were new, the rated power of the panel was 210 watts. Now it's 2024, or in this case, we are simulating for 2022. The rated power will not be 210, so we'll need to account for that. And for that, we'll need to assume some kind of degradation rate and degradation model. Otherwise, we'll overestimate how much the panels have actually produced, and we need to basically account for aging and other degradation happening. So let's start with the stuff. So we want to, for these 2 weeks that we've used in the previous exercise, we want to model what is the output of the panels, and then we will compare with the actual output of the panels. So the first step will be to close this. First step will be to let me see. Determine the rated power and the temperature coefficient. Now, the temperature coefficient we can get from the data sheet. So this will be 0.46% per degree Celsius, minus 0.46% per degree Celsius. Whereas the rated power in 2008 was 210 watts. So we need to account for that degradation. How do we do that? Let me reconnect here. Okay, I think I need to. Maybe I will connect this one. Yeah, sorry, I need to run these things again. This. Or maybe I'll use this one here. Okay, so we were somewhere here, right? Exercise 2. So in order, I'll just go through the solution because we are a little bit behind. So as I said, in 2008, the rated power of the panel was 210 degrees, but it's been a few years since then, and the modules degrade. How much they degrade is difficult to say. Usually, we can assume a typical degradation rate, and the average degradation rates for crystalline solar panels is 0.5 globally. Now, if you are in hotter environments, it can be higher. If you're in lower temperature environments, can be slightly lower. So we'll assume a 0.5 degradation per year. And the modules have been operating since 2008, and then we are calculating the performance in 2022 when we have our weather data set. So we'll need to basically compensate or derate our Pmax power by this degradation rate. Whereas the temperature coefficient would just take from the data sheet of the panel, as I showed you here. It says the temperature coefficient is minus 0.46. Okay. Then we'll need to determine the rated power of the PV array. So we need to multiply. We know this one has 36 modules, 18 in series and 2 strings in parallel. We multiply 18 by 2 by the rated power. Then we need to implement these two equations, 8 and 9. We implement them both in this one here. So we have the effective irradiance that we've calculated in the previous demo, divided by the STC irradiance, multiplied by the rated power of the panel, and the temperature coefficient, and adjusted by the temperature. So now we have the power production of MPPT1 connected to inverter 1. Let's see how close are we to reality. So we load our data set. So our second data set that contains not only reference cell measurement, but also power measurements. Power measurements from all 4 inverters and all 8 inputs and all 4 outputs of the inverter. So in this case, we will need to compare our simulated value with the actual power measurement of inverter 1 MPPT1. So we'll load this data set, and then we'll compare the simulated power with the measured power for a clear sky day. And then it will look something like this. And then we can see they coincide pretty well. If we hadn't had this derating here, if we just had put 210, and then we go through these steps again, then you would get something like this. So you really need to account for the degradation of the panels when you are simulating an older system. Now there is still a little bit of difference here. This could be maybe spectral effects, could also be shading, or maybe slight differences in the actual tilt of the system. We don't really know. We don't see it in this part, but we see it on the other part. So it might be a slight difference. So the actual system maybe is not exactly 9 degrees tilt and 14 azimuth, maybe something else. So that's why we could see a little bit of difference between the modeled and the measured values. Could also be maybe a difference in the times. That's also possible because they are measured with different systems. Okay, so that's pretty simple equations, easy to implement. Now, pvlib has a lot of models, and it also has this power temperature coefficient model. Sometimes is also called the PV watts models, and it's exactly the same equation. Of course, pvlib has also other models like the CIC, the Sandia model. Those can be a bit more complicated, require more parameters, so you really need to know why you are using them. For most purposes, if you have the datasheet of the panel, this one is good enough. If you are modeling some peculiar thin film technology, or you need to model the entire IV characteristic, then you might need something else. Okay, so if we want to use the PV system one, pvlib one, there is a PV watts DC, and it's exactly the same power temperature coefficient model where you give it the effective irradiance, the cell temperature, the rated power of the array, and the temperature coefficient. And then you get basically the same as with the equations. So this was for modeling the solar cell, the PV array performance. Do you have questions on this? Otherwise, we are 14 minutes behind, so I'll just continue with modeling the inverter.